there. Oh, thank you. I think it is there. Okay. Okay. All right, for those that are online, can you see my screen okay? Okay, great. Thanks. Okay, so last time, still need to figure out how to not let it freeze. Last time we talked about RLC. So anyone want to take a stab at writing, like summarizing the procedure to solve for RLC circuits? Go for it.
You just take what you already know, and you can use substitutions into those other equations to find the second order differential equation.
Okay.
And then you can go ahead and solve that and use your initial conditions that in order to find, you have to note that the voltage on the capacitor and the current of the inductor don't change instantaneously.
Okay, so in order to determine though which set of equations, you need to know what? So series and parallel is one thing you need to know. What else do you need to know?
Like the level of damping, is it overdamped, critically damped, underdamped?
Correct. And what determines those? Correct. Alpha and omega. Yes. So the damping coefficient, alpha, and omega naught, which is the angular frequency. So you're comparing those two to determine overdamped, critically damped, or underdamped. And then you have the equations also for alpha and omega. So then, quick summary, identify series or parallel, and you identify it in the final form. So that is going to be the configuration you want to determine because it may be different in the initial versus the final. And so calculate omega and alpha, and then compare, determine overdamped, underdamped, critically damped, find the unknown variables for the equation set that corresponds to those, and plug into the equation. So then we looked at this circuit, which was a series RLC, and we found alpha, omega, and they ended up being equal, which put us in a critically damped condition. And then we found the coefficients for B1 with the initial values, the final values, and plug those in. Okay, you guys ready to try another one? Okay, so we're going to try this one. So at time, yes?
On exams, are you going to give us those charts of like underdamped and overdamped, or is there like a link to it?
So you will want to have your own link to it. So it is on the, let's find the, so there's two locations for where it is. So there's one on the lectures itself, and on the lectures, when you go to the handouts and lectures, there'll be the RLC circuit equation table, and that link is that whole table. So it's there, or it's also in the learning module itself. I usually put those at the top of kind of the learning module. So important table, RLC. So it will be there too. So a couple locations, do know where it is or have it printed out, whichever one you feel more comfortable, because it will be very handy to be able to use that. Hard to solve if you do not use that. Okay, so go ahead and break up into small groups of individuals, introduce yourselves for if you don't know the people around you, and go ahead and try and first identify what configuration the circuit is, and then try to solve it. So right before that, what's happening here? So that's one of the things you have to interpret, like what is going on here? So when you see the switch, the arrow means what? It means where it's going to. And so in the initial condition will be with the switch to the right of it, and the final is going to be when it's just going to the left. Okay? And for this, you are trying to find IC of t greater than or equal to 0. So comment on this is you first need to find VC of t and then relate VC of t to IC of t. So find the equation first for VC of t. Okay, so that's the hint. And I will label the polarity as plus on top to minus on the bottom.
And are you guys met?
It's using the equation
For a while, just assume that the voltage response is naturally zero.
We don't know.
Oh, it's L. Yep, it's L. You're right.
V naught. V naught's 40 volts. We know the IC is. We don't know.
I totally understand. But that's what we're talking. No, that's great.
We have to solve for that yet.
I guess this is still.
We know that it's RLC in series. So, we believe in series we solve for current.
Yes.
All right, so before people get too far, is this series or parallel?
Series.
Okay. So correct, it is in series. So that's the first thing to identify. So do make sure that you see that it's in series. So again, to determine that, it is in the final position. And so in the final, you're going to have this circuit. So series.
One of the square roots. Yeah, so, no, that's the last time.
Yeah.
There's no round.
Yeah, so in this case, we already, it's just given us points.
Oh.
Once that switch is closed, you just have that series.
What about size series or for parallel? What's your next?
10 radians per second.
We're finding some, yeah, alpha and omega squared.
Need alpha and omega charge. So you're gonna write down the alpha and omega based on series or parallel. So equation.
So alpha for series is
That's just the
RTH over 2L.
So it's not two classes, so.
So that's going to be C1 times e to the negative e.
What's the capacitors charge that acts like
e.
right? So it'd be, yeah.
So RTH over 2L.
And omega is square root of 1 over LC.
Yep.
I just wrote it down. See how very practice. Yeah. I need to make a list of all these formulas.
10 millifarads.
You just look it up. I think she has a list of
1 times 0.01, and then we're divided by that, because that's gonna give you 100, and then you, because 1 times 0.01, and then you 1 divided by 0.1, yes, so 1 divided by 0.1 would just be 10.
Yeah.
That's gonna give 10 radians per second for the
And so
Omega naught and R and alpha are equal, so it's, yeah.
basically she
That's
has
pretty
it.
good.
If you can find it somewhere.
And then we know that the capacitor voltage as it goes to infinity is gonna be 0 because there's a resistance in that circuit, but no voltage source. So it's going to take the C1 plus C.
If you with all our videos and lectures,
Or C1 to the negative 10t plus C2 to the negative 10t.
Would you say go to overview?
yeah, overview.
That comes from solving the differential equation. You can just look it up.
And then at the bottom.
Okay, that's what I meant.
Yeah.
I memorized that.
So for B1, you guys
The
got
RTH is just 20.
I've got, in my mind, I'm visualizing all the different.
Oh, is it for initial or final?
I have way too much.
So what's the minimum
Have solved that.
or are we just solving it?
Well, we're trying to determine which equation to use out of these by if alpha is greater than omega or less than. Like it gives conditions. But we just want to look at the series column.
So now we know that this is going to be IL. No,
We have a
VC.
resistance and no current.
Okay.
So are we getting this, are we getting L in terms of?
So now what we're gonna do is.
Oh,
we
but we
know
need
that
an equation.
We know that VC is 0, 0, right? So we plug in 0 for this, that gives. When
Is there a resistance?
VC is 0, it's going to give us. Plug in 0, C1.
So RTH would just be 20 volts.
I was just trying to think if there's a
Well, isn't
Now, we know that 48
and then
omega times that.
Omega is
So that's going to be
square root of 1 over
what's negative 1. Is that C1 million?
No.
Yeah, I'm pretty sure they're all.
Oh, yeah.
So they're equal, so we make it clear.
Well, that's our final question. Now the question is, remember how we get voltage current.
Yeah.
That way it works out.
So when you say this equation,
Yeah, I think we just gotta find out which one we need to plug it back to the top.
It was a fun conversation.
okay,
Everybody's like, oh, she's cool.
zero, but you pull that out right there.
You see it, but you would be.
Yeah.
Yeah, I think so. Yeah, it's the same part in
This part, I'm not sure if I can
That's
that's a non-zero quantity when I'm dividing. But that's negative 10 plus plus.
It's really surprising that none of us, well, like, yes, to what extent has it been
If I remember correctly, if I would have equation for current. And
with the current.
we just need to take the derivatives of this chart of all this.
Yeah.
Oh, yeah.
Okay, so then it's just 40 times.
Wait, yeah, you're right, you're right.
Okay.
So I like that number. Because I'll be gone all of So I'll be around. I can go. If you want to.
That's our answer. Or do we need a?
I mean, we're just trying to find, so. Yeah, we can. It's not this one? The critically damaged cars? Do we just do the same thing? So then E1 is. Which one are you looking at?
This one. We just do this.
The one over here is for parallel. So we have to stay in this column.
Oh, yeah, you're right, it is.
Yeah. Oh, yeah. Okay.
Oh, DPT2. So I equals LC. Or just this. Or that's what I thought.
So P2 is going to be 1
Wait, if we just multiply the number.
That one, why did you?
Oh, yeah, we do.
I can never remember that.
But you can have a positive part of your so you just have negative 4. Yeah, but then. So that's
What's the capacity size again?
10 millifarad.
Wait, so you multiply it all the way across to the
It would be so helpful. I can just remember.
I do it with zero. When you get 10 times all of that. That would be
It's much more simple.
That would be my thing.
Do I have to take math or something? There were so many, my professor was so sweet. This is called and we're like,
Yeah. So can't give us the
Did you like your final equation I'm almost there. It's just really weird. So
Better than the slide. Well, and I opened up the little quizzes last night, and that was easy. And then
Are they just the same form?
oh, it was the homework. Yeah.
Oh,
the
just homework quizzes?
tape. Yeah. The homework.
So you haven't taken like the quiz
No.
thing?
Although I actually.
I'm pretty sure at the time.
I was like, I thought it was past due because it was like 12:03. It's like due at 11:50. Yeah.
And then you just adjust. That's gonna.
So we'll see.
But I'm pretty sure we get drops and stuff. And the midterms are like 75%.
I love that.
Yeah. With the final mistake, especially.
Yeah.
That's huge.
Okay, so alpha is in what units?
Meters per second?
Correct. Okay. Omega naught units?
Radius per second.
Okay. So you use the equations for alpha and omega naught based on if they're in series or parallel. For series, alpha is RTH over 2L. Note that it's different for parallel. So for that, you can go back and look at it. And for parallel, it's 1 over 2 RTHC. Okay, so do note that they're different. You should have found that alpha ended up being 10 nepers per second, and omega naught is 10 radians per second, so critically damped. So with them equal, critically damped. Did you guys all find critically damped? Saying yeses. Anybody have any issues getting that?
This is just like
Okay.
a zero question, but
Uh-huh.
where they're different units, are we just comparing the magnitude of alpha and omega?
Yeah. It's just the magnitudes of them. And they actually are similar because they're frequencies. But they're different, yeah. So, yes, just the magnitudes. Okay, critically damped. So then we need to know for critically damped, VC0, VC infinite, which is the final, VC0 is initial, IC0 is the initial value, VC0 is initial, and then final. So the initial circuit is at T equals 0 minus. And so redraw the circuit, leave out the switch, leave out the elements, and then decide at that time what each of those is doing. So at T equals 0 minus, that's before it's moved, so it's going to go to the right. So I drew that one in. And then it sat there for, you assume it sat there for a long time. So capacitor is open, inductor is a wire. And so looking at this and analyzing this circuit, I can see that IL is 0. So that would be my initial value for IL of 0. And VC is going to be the voltage, because there's no current flow through that because it's open and a floating wire. So it'll just be 40 volts for VC. Yes.
Why would the inductor be a wire if there's not current flowing in it? Like, wouldn't it be uncharged then?
So if you just take an inductor just sitting from you take it and you measure it, you measure the voltage across it, it looks like a wire. So it's the same thing, when you have it in a circuit and it's sat there for a long time and not ever been charged, and you just like pull it out of the drawer, it will look like a wire. So we kind of model it as a wire. I mean, it will be 0.00001, kind of a thing if it has a little charge on it. But it's literally like we just kind of model it like a wire. So even though it doesn't have charge on it, it still can act like a wire or an open. So if like a capacitor, you go and you're going to be like, oh, it looks like an open if it sat there in a drawer and I just pulled it out. So, okay. So IL will be 0, VC will be 0. And then the initial value, note, is always going to be, if it's not the voltage across the capacitor or the current through the inductor, it will always be the actual next step, which is that you keep those values the same. And in this case, the current for the inductor becomes a current source, and the voltage becomes for the capacitor, it becomes a voltage source of whatever that initial value is. So, sorry, this is 40. Okay. Let me rewrite this, sorry, because this will be 40 volts, not 0, sorry. So it is the same value as you find, and it stays the same. But because the current source is forcing that to be 0 current in that branch, it still stays 0 for the IC current. Okay? Yes?
So on some of the problems before, when we just had like RC or RL, we didn't really have to do this T0 plus.
Yeah.
So what is the requirement that we need to draw up the T0 plus?
So
Like what information do we get for that?
if it's not an initial value over the capacitor voltage or the inductor current,
Okay.
then you always need to draw it and figure out what is that value.
So, that makes sense.
So you'll want to just double check when you do this and not just make an assumption that that IC was 0. All right, was there another hand?
I was like,
Yes.
does that mean like in the sense of, I know in this problem it doesn't really make sense, but if you were asking for the current through one of the resistors,
Mhm.
we would need to do the T0 plus step.
Mm-hmm. And that would
Prior
be
to that.
its initial value, correct?
That would be the initial value.
Yep.
Which is when it switched.
Mm-hmm.
Okay.
Yep.
That was-
Okay. Final state, redraw the circuit again, leave out the switch and the inductor and capacitor, and then look at where's the switch. So going back to the original circuit, my switch is now on my left side. So I draw that connected to the left side. Capacitor again sat there open, inductor short. And so this will be my circuit for the final. And I have open circuit. So current's going to be 0 and voltage will be 0. And then I just basically plug these in. So VC of 0 is 40. VC of infinity is 0. And then IC of 0 is 0. So I plug those in and get this equation. So now I wanted IC of t though. So how do I find IC of t from here? Correct. Mm-hmm. So C dV dt is going to give me that IC. So my derivative of this is going to be what? So this is kind of like, or I can rewrite this. Let me write this is. So this is written as 40e to the minus 10t plus 400t e to the minus 10t. So I can take the derivative of the first 40e to the minus 10t. And so a derivative of an exponential is, how do you take that?
Keep it the same and then multiply by the derivative of the power of the exponential.
Correct. So I bring down minus 10 from the power portion of it. So whatever coefficient is in front of the t there. And then it just remains it's the same. So it's minus 10 times 40e to the minus 10t. The second one, you have to use the rule where you have terms, two quantities of terms. So you can take the derivative of the first term, leave the second term, and then add on the derivative of the second term and leave the first term. So the first term derivative will be 400, and then I leave the second term alone, and then I leave the first term alone and take the derivative of the second term, which is a minus 10e to the minus 10t. Okay, so then note the minus 10 times 40 is going to give me a minus 400. So that's going to cancel with this one. And I'm going to be just left with a, correct. Okay, so that's the derivative, and then the IC of t portion of that will be multiplied by C, which is 10 milli, 10 to the minus 3. And remember, this is for everything greater than time of 0, so I can put u of t on this. Yes?
Never mind, I figured it out.
Okay. So this ends up being a minus 40t e to the minus 10t u of t. So what is the current at time equals minus 1? It's true.
You can't figure out this one's 0.
It'll be 0, correct. Anything before time 0 is 0. Okay. What about at time 1? What do you do to find that?
Plug in 1 as t, so it'd be negative 40 times e negative 10.
Whatever value that is. Okay. All right, questions about any of this? Any questions? Yes.
So for B2,
Uh-huh.
why is the IC 0 again?
So you find that IC of initial value at time t equals 0 plus.
Okay.
So do you understand that part?
Yeah.
Okay, to get 0 plus, you redraw. So the trick with this one is substitute your inductor is a current source, and your cap is a voltage source of the step right before. So you found above IL was 0 and VC was 40. Okay, so do you see from that, because the current source is driving that of 0, there's no current flow in there. And so IC is going to be 0, and that's the initial value you use.
Okay.
So that's where IC was, you found 0 from, okay? Is that clear now? Okay.
Why do you have to find the initial value from 0 plus instead of just 0?
So because we're actually finding this after the switch, and we want to know like what is the rest of the equation. So because we're finding it after time 0, meaning that it's after the switch. So we're kind of looking at that time right at the switch time is the initial point.
But it's still like nothing should really change in that interval.
It could,
Well, it could for other, like he was asking about the resistance. So like the voltage across that resistance is going to change between, like across the 20 ohms is going to change because in the 0 minus it's 0, but then right as I switch it to 0 plus, that voltage of the capacitor of 40 volts is across it now. So that initial value would be 40 volts. So if I was to draw the circuitry of the 20 ohm voltage, that would start at 40 and then it would drop to 0. But if I look at the time right before the switch, it's still 0, so it would look like 0 to 0, but it's not really, right? Because it's starting at 40 right at the time of the switch and going down. I don't know. Hopefully that helped. Okay. Another question I saw?
I said the final exponential function we derived, if we were to draw that, I was just trying to visualize, would it be concave up or concave down? How does that look? If you don't know, then that's okay.
I'm actually gonna pull up my calculator.
Thank you, because I don't know if I could see. So what does it look like?
At first it dips down.
It goes to minus 40, right?
Not actually it's minus 40. The lowest value it gets to is -4 times e to the -1. So that it doesn't get past like -2. And that happens at 0.1 t, and then after that it kind of swings back up and asymptotes out to 0.
Huh. Okay. Yeah, I can't visualize that one, but graphing it.
Well, it's gonna be
Yep.
more simple, but yeah.
Yep, graph it and then you can see. Okay, any other questions? Oh, there's a question online. Oh, okay. All right, any other questions? All right, attempt another one. Oh, okay, need to go to the next notes. Lecture 3. Okay. All right, let's look at this one. We want to determine IC of T. Wait, I think 6 point. Do anybody have the notes? Which number is the one on the notes? Anybody have the notes up?
I think it's 2.4,
6.24.
6.24.
Okay, that's what I was thinking. Let me find. Nope. Okay, here we go. 6.24. Duplicate. Okay. Okay, so 6.24. We only have 5 minutes, so I'm going to run through this pretty fast. So identify, so let's just kind of do this together. You guys give me input. Series parallel. Yes.
It's looking like it's going to be series again.
Correct. Okay, not sure why that. Huh. That is weird. Okay. Not letting me redraw it. Not sure.
Would it be easier if we just, if we just represented the current source in that 0.01 ohm resistor on the left-hand side, if we just switch that out with the Thevenin voltage source equivalent?
It is up to you. I do not like Norton. So I end up just leaving them and then do node voltage with it. So that's my preference, but again, like, you can take that Thevenin and just be like, okay, 4 milli times 0.1 is gonna be the voltage, and then 0.1 is gonna be the ohms, which is the, you know, changing back and forth between Norton and Thevenin.
Well, right now it's
Um,
Norton, I was thinking
yeah.
switching to Thevenin.
Yeah, so you could do either that, or you can just leave it and then just say like, okay, I'll show you node voltage. So one is to identify, you know, what is this? So the final time is going to be open here. Oh, that is really big. Okay, so an open, and then you look at the capacitor and the inductor, and you can see like, okay, yes, they are in series in comparison to each other. So that's where the series comes from. And then we want to find the initial circuit. So initial is going to be with it closed. So redrawing it with all of these removed, and then this will be an open wire, and this will be short here. So we're going to do the same thing where we need to first solve for VC to find that IC. So VC in this case will be, yeah, I'm not going to get through this in 5 minutes. This will be 0 here, and then I'm going to, oh. I don't know where they went. That is really weird. Okay.
I saw you only had 5 minutes and gave up.
I know. Oh my. Let me see if I can go find it again. Part 3. Okay. Nope, that's not it. Okay, this one has them drawn on it. All right, so VC of 0 minus will be my initial circuit. And then this I can see is going to be an open. And so 0 current flows through there. And I can see that this is all the same wire. And if there's 0 volts there, that becomes all the same wire, right? And then I can put ground over here, and I can call this top one VC and do node voltage for minus 4 milli plus VC over 0.1 plus VC over 0.1, and that equals 0. And then I can solve this for VC. And that can give me a value for my initial value of 2.2 milli. Okay, going to the final one, I need to find RTH to be able to find alpha and omega naught. So with that, the final circuit is open, I think. Yeah, open. So this is going to be a dangling wire. And I need to, what happens with the current source for RTH? Okay, so this will look like an open. And then my pathway is going to be from one side to the other side, A to B. And so in order to do that, it becomes a little confusing, right? Because you're like, okay, I have something floating here and something floating here. So what I recommend is always put the RC next to each other. And remember, in a branch, you can move elements. So this is the same as this. And then it's easier to say, okay, I can put my A to B here and then take the pathway around. So this would be there. It goes there, and then this one has this. This is 0.52 and 0.1.
So Thevenin resistance equivalent to be 0.62 ohms?
Correct.
Why does that work?
Because current through these are all the same, right? This current and this current goes through each of these. So it's the same through each of those elements. What's different is the voltage drop across all of them. But if you sum up everything, the voltage between here and here is going to still be the same. It's just, if I have 9 volts and I have 5 volts, the whole drop across it is 15 volts. Wait, 14 volts. 9 and 5.
Total amount, yeah.
Yeah. And I could go like this, and it would be the same across the whole thing. Current could flow through this one and this one. So it doesn't matter which order they're in.
As far as like resistance is concerned.
As far as, yeah, like an impedance. So we look at the inductor and the capacitance as an impedance, just like we do with resistors. So with impedances, we can move them throughout the circuit, throughout a branch. And they're going to be the same currents going through all of them. It's just, here I might have 5 volts and here I might have 9, but the total drop across the whole thing is the same. And so because the drop is the same, it doesn't matter if I do 5 up here or 5 below, if that makes sense. Okay. So this is how we can get to where it's easier to look at that and say, yeah, they're in series and it's going to be 0.62. Okay, Monday we will continue on with this and we'll solve, you guys will get more of an attempt at solving this, and then we will work together to solve the rest of it. Have a great weekend. Again, reminder to do the quiz if you have not yet. And Jagan, I apologize again for the quiz last night. All right, any questions online? Okay, have a good day.
Then we're saying that because of the way that we're calculating the resistance, we can move them along and move